Hi there. This video is going to walk through how we start to combine atomic orbitals to form molecular orbitals. So this would be considered our LCAO-MO theory. Okay, so there are a few rules to keep in mind as you start to combine atomic orbitals to form molecular orbitals. Okay, so the first thing to keep in mind is that only atomic orbitals of similar energy and the same m sub L values will combine to make molecular orbitals. Okay, so not every orbital is going to be able to combine to form a bond. Okay, so you can't take a 1s orbital and form a bond with a 3py orbital. Okay, it's just not going to happen. So you have to be in similar energy and same m sub L values. So we're looking at things like a bond between two 2s orbitals. Okay, so same value of energy and same value of m sub L. Okay, same with a 2s and a 2pz. Okay, you could form a bond there. So again, same values of energy and m sub L's. Okay, so again here, one thing to note is that by convention, your z axis is going to correspond to ml equals 0. Okay, as will obviously your s. You only have the one orbital that's going to get an m sub L value of of 0. Sorry. Okay, and then the x and the y coordinates will have your +1, -1. It doesn't really matter which label you give them as long as you're consistent throughout your entire molecular orbital process. Okay, so the next thing to keep in mind is that the number of molecular orbitals that you make must be equal to the number of atomic orbitals that you combine. Okay, so if you are combining the 1s orbital on one atom with a 1s orbital on another atom, you are now combining two atomic orbitals, which means you're going to make two molecular orbitals. Okay, so we'll see in a little bit that that means that you're going to make one molecular orbital that is lower in energy, okay, or kind of favors bonding of the two atoms, and then you'll make another orbital that's a little bit higher in energy. We call that an anti-bonding orbital, okay, that does not favor bonding between the atoms. Okay, so you'll start to see that the relative numbers of electrons that you have in bonding versus anti-bonding orbitals is going to essentially dictate the likelihood that your atoms are going to come together and form a bond, or how stable that bond is that you can form. Next thing to keep in mind is that our molecular orbitals get labeled just like we label our atomic orbitals. So remember, for atomic orbitals, we have our SPDF labeling system. We're going to also label our molecular orbitals, and they get labeled according to their m sub L values. Okay, so if you keep track of the absolute value of your m sub L, okay, then you will be able to assign your sigma, your pi, and your delta. Okay, so remember, it's based on the m sub L value, so that means that you can have sigma molecular orbitals that are created with p orbitals, right? So if you have your p orbitals, those pz orbitals, okay, those are going to be m sub L's of 0. Okay, those are going to combine to make sigma bonds. Okay. However, if you're looking at your py or your px p orbitals, you can probably picture these hopefully in your head from again, organic chemistry or Gen Chem bonding picture diagrams. Okay, those overlap in a way that creates that pi bonding where you get the overlap above and below your nucleus. Okay, we're going to take a look at those pictures in a minute, but again, just pointing out it's your m sub L that dictates the sigma, pi, or delta labeling. Okay, we're pretty much going to be working with just the sigma and pi options with our cases. Okay, Next is considering the inversion symmetry of your orbitals with respect to the center of the molecule. So if you have a even or symmetric symmetry upon inversion, okay, you get a label of G, which stands for gerade. It's the German for even. And if you have anti-symmetric functions, okay, so essentially if your signs change upon inversion with respect to your center of your molecule, then you get a U label, which stands for ungerade or odd. And you've probably seen these labels popping up when you talk about molecular orbitals in other classes. So this is giving you a sense of what those actually mean. All right, and lastly, our anti-bonding molecular orbitals are going to have a nodal plane, which is perpendicular to the internuclear axis between your two nuclei. Okay, we label our anti-bonding molecular orbitals with an asterisk, and again, this is just kind of reminding you that you can have a node in your molecular orbital that does not necessarily indicate that it's anti-bonding. Okay, so if your node is along the internuclear axis between your two nuclei, okay, that's not going to be considered an anti-bonding orbital. Again, we'll see some examples of these with some pictures in a minute. Okay, so we've already talked about previously how the approximate electronic wave function for hydrogen is a product of two H2 plus-like wave functions. Okay, so this is, again, is exactly analogous to approximating our helium atom wave function by the product of two hydrogen-like wave functions. Okay, so we are essentially combining a 1s type orbital on atom A and a 1s type orbital on atom B. Okay, so we have this picture here. So here's a 1s orbital on this hydrogen and a 1s atomic orbital on this hydrogen. Okay, so we have two atomic orbitals that we are combining in this case. So that means that we're going to be making two molecular orbitals. Okay, so the two options for those molecular orbitals, again, are going to be dependent on whether we have constructive or destructive interference. So we talked about that overlap of our wave functions in a previous video, okay, where you can have overlap of two positive functions or overlap of the positive and the negative, okay. So you can refer back to that video as a reminder. But that's what gives rise to our two atomic orbitals that we generate when we overlap two atomic orbitals. Okay, so when both of the s orbitals are the same sign, as in this case, then we get that constructive overlap, and we get a molecular orbital that looks like this, which is basically a big smeared out blob of those two 1s orbitals. Okay, so this essentially shows that we have bonding, right, in that middle area between our two atoms. Okay, and in this case where we have the different signs of wave functions or orbitals overlapping with one another, we get that destructive overlap, and we get no overlap in between our atoms, and that creates a node. Okay, so again, for this anti-bonding molecular orbital, note that we label that with an asterisk, okay? But this is that nodal plane that's perpendicular to the internuclear axis, which runs parallel, okay? So here we've essentially got our atom nuclei there. So that's our internuclear axis. So if we are perpendicular, as we are in this case with our nodal plane, that is what represents an anti-bonding behavior. Okay, you can have a node along this plane right here. Okay, along this axis. All right, that's not necessarily going to be an anti-bonding molecular orbital, as we'll see in some other examples. Okay, so another way to represent these molecular orbitals is with what we refer to as a molecular orbital diagram. So you have most likely encountered one of these diagrams in another course in your chemistry careers, so hopefully this looks familiar. So what we're doing here is we have atomic orbitals on the outside here. So here's the atomic orbital for atom A. Here is the atomic orbital for atom B. Those are both 1s orbitals. Okay, and each one of those atomic orbitals contributes one electron. So you'll see that we've got one electron placed in each of those atomic orbitals on each atom. And then in the middle, okay, here is where we draw the resulting molecular orbitals that are generated by combining those two atomic orbitals. Okay, so molecular orbitals go in the middle. Okay, so what we're doing here is essentially creating an energy level diagram for all of the orbitals that we have. So atomic and molecular orbitals are both represented in this type of figure. All right, so the way we put these types of figures together is by accounting for all of the types of molecular orbitals that we create when our atomic orbitals combine together. Okay, so in the case of our hydrogen atom, we have our two 1s orbitals from each atom. Okay, so those are represented in our diagram with those lines on the outside. We have our two options for how these orbitals will combine. They can combine either constructively if they're the same sign, or destructively if they are opposite sign. Okay, remember we already talked about that in a previous video with the signs of our wave functions and how we get the constructive or destructive interference based on the sign of each wave function that's coming together. Okay, so we essentially generate one orbital that's going to be lower in energy, okay, which we'll put right here. So this is our lower energy bonding orbital, okay, and then we generate another orbital that's a higher energy with respect to the individual atomic orbitals. Okay, so this is the higher energy anti-bonding molecular orbital that we generate. Okay, so we have two atomic orbitals coming together to form one lower energy molecular orbital, a bonding orbital, and one higher energy anti-bonding orbital. Okay, and then the next step would be to place the electrons into your molecular orbitals. Okay, so again, you're just going to do an accounting of the number of valence electrons that you have coming from each atom. So from atom 1, we have one electron. From atom 2, we have one electron. So that means we're going to have a total of 2 electrons to fill our molecular orbitals with. And you'll follow your Aufbau principle, your building up principle, and your Pauli exclusion principle, where you get 2 electrons in each orbital and you fill low energy to high. Okay, so those 2 electrons are going to start off down here in our lowest energy molecular orbital. And that's it. Now we're out of electrons. Okay, so all of our electrons are in this bonding molecular orbital. Okay, so that tells us that bonding is a favored situation for these 2 hydrogen atoms. Okay, so by coming together, they have lowered their energy, their respective energy, versus staying apart. Okay, so this tells us that hydrogen likes to be in a bond versus as an individual atom. So it's going to spontaneously form a bond if it gets close enough to another hydrogen atom. Okay, so we would repeat that kind of process for all of the different types of atomic orbitals that come together to combine in a particular molecule. Okay, so you'll have any combination of s, p, d, f orbitals that might be combining into molecular orbitals. So these are just a few pictures that hopefully look familiar to remind you of the kind of interactions that we tend to see for our formations of different molecular orbitals. Okay, so here would be the overlap between 2pz orbitals. Remember those, we're going to call this horizontal axis our z-axis, okay, just as a convention. So these would be the overlap of let's say negative and positive and positive and negative. Okay, so if you have two p orbitals kind of coming together in that orientation, okay, you would get, hopefully you can see that you would get that constructive interference and overlap there, okay? So that would be a bonding orbital. And then in this example above, let's say we have minus, positive, and following the shading, that means that this is minus and this is positive. Okay, so in this case, we have that kind of destructive interference right here in that overlap area. So that's going to give us the node right there. That's going to be an anti-bonding orbital. And these would all be sigmas, right? So if you remember your definition of sigma bonds, we also call that head-on overlap. Okay, that's overlap that happens along the internuclear axis. Is another way to identify those. Okay, if we look over on this side, we can see different types of overlap with our p orbitals of different orientations. Okay, so here we have a couple of options for how these p orbitals are going to overlap. Okay, so if we have the same, I'll draw it over here, the same signs coming together like that, okay, we would get that constructive overlap above and below our internuclear axis. Okay, that creates our pi bond, right? So remember, pi bonds are above and below. That electron density is above and below your internuclear axis. Okay, and that's, again, distinct from your sigma bonds, which are where your electron density is right in the middle, right between your two atoms. Okay, other option, right, is if our signs are different. So if we have plus, minus, and let's say this one was oriented the opposite way, when they come together, you get that destructive interference between these two lobes, and then we get that node in the middle. Okay, so that would be representing our anti-bonding pi orbital. Okay, and now let's look a little bit more closely at that idea of center of inversion and what that means for our labeling of these different orbitals. So again, notice we need to also factor in that G or U label for our different molecular orbitals. So basically what you want to do is, number one, make note of the signs of the different components of your molecular orbital, and then flip it inside out, okay, with respect to the center of your molecule. Okay, so if we take the situation where we had two s orbitals of the same sign coming together, okay, so we get that constructive overlap in this case. If I flip this molecular orbital inside out with respect to the center of my molecule, ask yourself, does the sign change when I do that? Okay, if the sign does not change, then you have that G, or that symmetric label. Okay, so you're asking yourself here, does the sign change? Okay, so here sign doesn't change upon inversion. Okay, so that means you get the G, symmetric. Okay. Other option, right, was when we had two different signs of those s orbitals coming together, so positive 1s orbital, negative 1s orbital combining. That was our anti-bonding. We get the node in between. Okay, so to get our labeling there for the symmetry, again, just flip it inside out with respect to the center of your molecule and ask yourself, do the signs change? Okay, so in this case, if I flip this molecule inside out, this negative is going to end up over here, and this positive is going to end up over here. Okay, so in this case, the signs do switch. Okay, and that gives you that antisymmetric symmetry, okay, which we label as U. Okay, so things are a little bit more interesting when we look at the p orbitals. Okay, so these were the two options for how our px or py orbitals could overlap with one another. Okay, so in this case, again, you're just going to switch the molecule, sort of flip it inside out. So go to opposite corners. Okay, so when we invert here, it's not an inversion across this mirror plane, right? It's an inversion across the center of inversion. So we're going to flip it inside out. So this corner is going to go to this corner. This corner is going to go to this corner. Okay, and then ask yourself, what happens when I do that? Okay, so in this case, when this negative goes over here, I'm switching the sign. So this is going to go from positive to negative, and same with that inversion. Okay, so in this case, signs change, so we get the U. Okay, and then looking at this situation over here, if we flip this picture inside out, okay, about our center of our molecule, then we get these two exchanging, those signs are not changing for us. Okay, so that is going to give us the symmetric, or the G. Okay, so signs don't switch upon inversion, so we get the symmetric G label. Okay, so again, a little bit of a mental gymnastics on this, but that is how you will come up with the labeling of the U or the G, so the antisymmetric or symmetric labeling for your molecular orbitals. Okay, so when all is said and done, you will be able to put together these sorts of molecular orbital diagrams for your various molecules. Again, we limit ourselves for simplicity here to simple diatomic molecules. Okay, so in these two examples are both for our various homonuclear diatomics. Okay, so both of the atoms are going to be the same species of atom, in this case for a homonuclear diatomic. And you'll see that your molecular orbitals, again, get filled low energy to high. Okay, so this is where we identify our HOMO, right, highest occupied molecular orbital. And then there's two lines there, so be careful. That's going to be our LUMO. Okay, and you'll see that a few of our orbitals are degenerate. Okay, so some of your pi orbitals, okay, will be degenerate in your molecular orbitals. So make sure you pay attention to those designations there. And then the last thing I'll mention on this slide is that it turns out that the ordering of your molecular orbitals actually switches when you get to a certain atomic number. Okay, so as your atomic number increases, it turns out that the sigma 2p and the degenerate pi 2p orbitals, they like to switch. So we're looking at these orbital orderings right here. Okay, so here you can see the sigma's on top, and over here you see the sigma is lower in energy for that situation. Okay, so it turns out as your atomic number increases, those orbitals get closer together in energy and eventually switch positions, going from molecules lower than or equal to nitrogen as you move to molecules greater than or equal to oxygen. Okay, so this is essentially the dividing line between nitrogen and oxygen. So atomic number of 5 versus 6. All right, so moral of the story is be careful to pay attention to which side of that switch you're on when you assign electrons to molecular orbitals. So you want to make sure that you have the correct ordering of your molecular orbitals when you're putting these kinds of diagrams together. Okay, and last little bit here is what things would look like if you are looking at a heteronuclear diatomic molecule. Okay, so you can see in this case we no longer have equal atomic orbital energy. So you see that those are offset because the energy for a carbon atom is going to be different from the energy associated with an oxygen atom for each of those types of orbitals. Okay, so those are going to be offset a bit. And then the other thing that you'll notice is that there's no U or G labeling on the molecular orbitals that are associated with a heteronuclear molecule. And I'll give you a second to think about why that might be the case. Okay, so hopefully you've maybe thought about what the meaning is behind that U or G designation, right? That tells us if it's symmetric or asymmetric upon inversion. Okay, ask yourself, is there any way to have a symmetric inversion in this case, right? There's not, all right? So no matter what situation you're in, there's going to be some asymmetry there, okay? So that's why you only see that U and G designation for homonuclear diatomic molecules. Okay, so that was your crash course in putting together molecular orbitals from atomic orbitals and creating a molecular orbital diagram. So this is essentially how you go about really trying to predict whether or not two atoms are going to form a stable bond. Okay, so what you're going to be looking at when all is said and done is the relative number of electrons in, I'll go back to this picture, the relative number of electrons in a bonding versus anti-bonding orbital. Okay, so the more electrons you have in bonding orbitals, the more likely you will be to form a bond, or the more stable bond you will form. Okay. And then you can do some really fun exercises along these lines and sort of picturing the molecular orbitals that are formed for different molecules using some exercises in Spartan. So some fun activities in store for you there. But for now, hopefully this gives you a nice overview of how atomic orbitals and molecular orbitals are related and how we can use them to predict bonding behavior for different diatomic molecules. All right, thanks.